is for Chris to just introduce yourself and talk about what you do, your profession, and how you got into wanting to build buildings like this.
Thanks, Jack. So a couple of workshops ago, I came here and it was a COVID one, and I had this interest in combining permaculture and architecture. So that was my takeaway from that workshop. A year and a half later, I'm working on it. And just every day, every night, early morning, late at night, I was sketching on, pondering on ideas. And at the end of it, it was a small deliverable. It was a PDF. I shortly call it Permaculture Concept House because it's easier for me to remember. And what it is, it's a prototype to me. It's a template solution for a custom home optimized for home setting based on permaculture principles that I can go and build later. Because our plan was to build a house. Um, Over time, we did sell our suburban house, bought a place in the country, and we put an RV there. We stayed a year studying the land and meanwhile designing the house. And I used those concepts to design the house. It took us longer because there was we needed a lot of reduction budget constraints. My wife has to, of course, agree with it's our house. We have to both have our say in it. It took longer, but when we finished it, we self GC'd it. Thanks to Jason, he pointed us to a company that would help us be the GC on the job. We finished it. We learned so much from the process. It's basically a lot of we were able to put in a lot of the ideas. Um, some constraints we couldn't, but for the most part, since we were out in the country, we had a lot of flexibility. So hopefully, the lessons I've learned from that experience I can share here with y'all. I hear Buddy is building one soon. I'd love to hear that as well. Maybe we can exchange ideas.
Okay, cool. Now, I'm sure there was a lot of you that had questions during Alan's talk. So now we need questions, and I got to go be Jerry Springer, so we don't squelch out. So we don't squelch out the mic. So if y'all could, anybody's got a question, come on over here. Here you go.
Thank you. Alan, my question was one of the last things that you talked about, and quite frankly, it has to do with building inspectors and it has to do with infrastructure, etc. You mentioned that they require for the natural water that it be chlorinated. And with all the research that is being done, why would they implement that and what would be their argument? Because I mean, I don't think anybody in this room would agree that chlorinating water is appropriate for drinking water. So that's my question to you. What is their response to that?
The fact was that all the regulations we're stuck with were written for municipal water supplies. Okay, so they were written. The problem is that most of these inspectors, what they basically is like, here are the regulations that you are required to uphold, right? And so they're some of them will flex a little bit, but most of them go by the rule that you won't get fired for following the regulations precisely. Okay. Yeah, it's a government employee. Yeah, and so they're going to follow the letter of the book. And so what they're going to do is they're going to come in the door and they're going to be like, well, the book says this, and that book was designed by people who were trying to keep municipal water systems safe and who were lobbied by certain constituents in commerce and industry to make it a certain way. Now, like, for example, in places in Europe, it's actually illegal to chlorinate water, and they have alternatives, ozonation. We did. One of the people I work with, Rebecca, she helped do a living building challenge building on the coast of Alabama that was pedal certified, one of the most aggressive green building standards in the world. They had to do all of their own water. They did rainwater to potable. They had everything beautiful. The water tested out. It was gorgeous. And the state of Alabama came in and said, well, per our regulations, you must chlorinate the last 12 feet of pipe. And they could not get them to budge. They went around and around on it. This is the stuff we run into.
Hey, to point out, there's two main plumbing codes which are used in America: Universal Plumbing Code and IPC, International.
IPC, yeah.
UPC is by far the most used. There is no rainwater collection written into UPC, which is why you run into that, because if there is no Universal Plumbing Code requirements, then it comes down to not just the state, but each individual municipality. And that's why you run into a bunch of those individual instances, because you have a local city inspector,
Yep,
which is making that. Now there is no governing body that dictates how rainwater catchment is done.
There's a joint standard committee standard out of Canada and US. It's been agreed to. There's a US and a Canada version. I forget the number. I've got it because I've had to comply with it. But it does allow for you to do this, but it hasn't been set up where it supersedes.
Right. It's allowed, and that one doesn't have chlorination.
That's
in
correct.
It,
Does not have chlorination in it.
So
We're
just
trying to
bear
get
in
that to
mind,
yeah.
look at it. It goes to state, and honestly, very few states will dictate. It'll come
Right.
down to your local municipality or mud district.
Yep.
So that's why the standards are all over the place. I actually taught the rainwater collection for continuing education in Texas for a
Yep.
couple years,
Yep.
and there is nothing saying that you have to chlorinate, but some of, especially these smaller cities and municipalities, require it.
Yep.
That makes sense now, because I was like, I don't understand this. I've lived on wells for the last 25 years of my life, and there's
Yep.
no such requirement for well water. And I don't see
Correct.
how it's any different.
Correct.
It's also different if you have both. If you're tying in your rainwater, which I'm sure is part of what you were hitting, because
Yep.
if you're on both a municipal water supply and rainwater catchment, if you don't have an air gap or some type of check valve,
Yep.
then it's just like if you have solar and you're on grid, you have to have
Yes.
safeties in place, because they'll let you poison yourself, but you can't
Yep.
poison anybody outside.
So what I will tell you is, if you are going to do your own off-grid water and you're going to do rainwater to potable, then what we will do is we will sterilize the piping once it goes in. So we'll do a flush to sterilize. We should always do that. So we'll make certain we do a really good sterilized flush. Then we'll clean it out really good, and then we'll start putting the rainwater through. And there you go. Because yeah, if your rainwater is done properly, there's absolutely no reason technically that you should ever need to chlorinate.
Okay, so in your talk, you did kind of be slightly different.
Yeah, so you're in the subtropics technically. You're in an interesting part of the subtropics. Most people don't, if they haven't been educated on climate zones, they don't think of places like this as subtropics, because there is frost. It does freeze, right? And so the technical definition most people go towards are like, yeah, the subtropics are technically supposed to be frost-free zones, but it's not that simple. This area in mid-Texas is technically subtropics, but it's right on the hairy edge. So it's subtropics that does get frost. So what you basically have to do is take a subtropics approach, but modify it to be able to handle frost events. That's really what you do, because the vast majority of time you're in the subtropics, right? So that means humidity is a big consideration. So in an area like this, I would be really leery of any kind of earth coupled building, like something where you had, dirt against the walls or whatever. We will typically go to pretty standard, like all of the ones I kind of talked about, like Timber frame works great. Cob works. Cob is not a good thing because you got long hot, and that long hot and cob is not a good thing. So I would not do cob. You could do straw bale here if you put a really good hat on it, which means that you put big eaves over it so that the water doesn't get on your straw bale. You can do hempcrete here. Hempcrete works very well here. Yeah, there's several other possibilities, but those are some of your best in terms of wall structure. Yeah, but I could keep on going, but we'll just leave it there.
One question online. Do you have a book? How do we get in touch with you, or how can we get your knowledge?
So the books that I'm putting out right now are hyper technical. They're not for this. They're not for that kind of audience. No, it's. We won't get into that right now. The courses that I'm teaching are through the institute, my institute, the Institute of Integrated Regenerative Design. Those courses are all professional courses, so they're designed for architects and building engineers and stuff like that. So those courses are typically taught at an advanced undergraduate or graduate level. And so, when I come and do stuff like this is when I'm having fun and talking to a broader audience. In a little bit less technical tone. So, yeah, sorry, I'm hyper geeky that way,
So I got one for you, Alan. As you saw some of the pictures at Tim's dome home, those look really interesting to me.
Yep.
And I'm doing some things with some land right now and making some plans in the future. And I thought of making a deal with those guys and doing some kind of referrals riff on it. And I probably can do that. And I can probably get one of them built for free, which would be awesome. However, you're talking today about the proper house for the proper place, hit home hard.
Yeah.
Are there places where you would say that's probably not the right type of structure?
I need to know a little bit more about it. I'm guessing that they're doing a vapor barrier inside the insulation. Excuse me, outside the insulation. If outside the insulation and outside the thermal mass, does anybody know? Or are they putting the insulation inside or out on the? They're putting the vapor barrier inside the insulation. Anybody know?
It's a PVC fabric.
Yep.
On the outer shell.
Okay.
The skin,
Yep.
and then they spray in the foam.
Okay. So there's a PVC acting as a vapor barrier. Okay, so they're putting the vapor barrier on the outside. So that is more of a southern U.S. approach. We can flip that sometimes in the far north for reasons I won't get into right now. And the PVC is a pretty hefty duty vapor barrier. So that approach is very possible. You have the advantage of thermal mass in areas where thermal mass inside of your insulation. So you can use that as a thermal flywheel to keep that. Once you got the interior at the temperature you want, that thermal flywheel is going to try to help keep it there. But yeah, I'd have to look at that. The way I looked at that, it's like there didn't seem to be any ventilation up really high in that. So chimney ventilation did not seem to be built into that. So that particular, there's a lot of advantages to that structure. It's a very strong structure. It's very robust. It's minimal material use. Therefore, per square footage, it's typically a little bit less expensive in the structure. All that stuff, great. But you're probably going to have some sort of active ventilation in that in order for it to perform. Just because there's no, in the way it's built right now, when I just glanced at it, it didn't seem to have any chimney effect, and I don't know how well it cross vents. How long does it? They have it set up for cross ventilation at all? Yeah, so they're probably going to use what's called a ERV, called an energy recovery ventilation system. And what happens is, any building you're going to build, you want fresh air in it, and you want multiple air exchanges per hour, and all these buildings that are built like a plastic bag, what they do is they have some way of exchanging air. And one of the most efficient ways of doing that is ERV, energy recovery ventilation. What they do is they pull in external air, and then they take internal air and they cross them over. And if it's cold outside and hot, and warm inside because it's wintertime, they'll pull the heat out of the pre-warmed air inside and dump it into the cool air coming in so that it's now pre-warmed before you bring it in. And then vice versa, when it's really um, cool, when you're in the summertime and you've cooled down the inside. Well, what they'll do is now you have cool air you're going to dump outside. They take that warmer air and dump the heat into it and then dump it out so it's pre-cooled before they bring it. That's called energy recovery ventilation. Okay. The heat exchanger, there's several different types of heat exchangers that they do on these. I won't get into all the technicals on them right now, but there are several different forms of heat exchangers in these energy recovery ventilation systems, right? They can be part of what's called a DOAS, a dedicated outdoor air system. But here's the thing. What I would do is I want to make certain that the CO2, not carbon monoxide, but carbon dioxide in the building stays below certain thresholds. I personally engineer a building to stay below 650 parts per million carbon dioxide. That's a very aggressive. The well building standard lets us go higher than that. What we see is by the time you hit about 850 ppm of CO2, you can measure the cognitive decline in the performance of people in the building. I've seen buildings where we can measure it, and when you get people into like an auditorium, we'll get 1200, 1300, 1400 ppm of CO2. Let me ask you this question. How many of you have gone to an event when you're in a big ballroom in a conference, like in a hotel? Everybody gets in there and you're about 30 minutes into the talk and you're just kind of going like this. You're like, I'm trying to pay attention. I can't. And you're how many have had that experience? That is CO2. That's what's causing that. And because those buildings were oftentimes built in the 1980s and the 1990s, they did not have demand ventilation. In other words, they didn't have a sensor. So what they did is they just set that big ballroom with an average amount of ventilation. And you put all those people in there and you close all the doors and they start breathing and they're just breathing out carbon dioxide. Okay. And what happens is that pretty soon it's just like up and up and up and up and up. And without demand ventilation, without sensors, it's like, oh, look at this. The CO2 is going through the ceiling. Then there's no demand ventilation to start dumping fresh air in there. And everybody's just kind of going like this, right? The same thing can happen in your house. One of my architects system, they could hit 1200 to 1300 parts per million CO2 in their bedroom while they're trying to sleep. And this was the reason they couldn't sleep well. And so they had to completely overhaul that and so forth. So this whole thing about it's not just a nice to have quality of life on really good ventilation and fresh air, really important. And so when I design buildings, this is something I take really seriously so that you can have a super high quality of life in there. Because yeah, we don't talk about it very much, but CO2 in a building builds up, and if you don't have that happening, you're not going to feel good in that building, and you're going to start getting mental fog and everything else. So be aware of that, and we make certain all of our buildings really, like, I don't let it go over 650 or 700 parts per million. We'll start dumping fresh air in there before we let that happen.
It's a cheap sensor, you can put your own HVAC.
Right.
It's just a CO2 sensor that you put in your return.
Yep.
And
it's called demand ventilation.
Well, assuming that the green options that you guys are discussing are the top end, what you would prefer to do.
Yep.
And traditional stick frame is in the bottom.
Yep.
A lot of us are kind of stuck with, just from practicality standpoint, of looking at what we think is great, which is spray foam and ICF, for instance. Would you scream at us that the chemicals are going to kill us, or do you think that's a decent compromise?
I have opinions. You have opinions?
So I forgot to mention mine is conventionally framed. The reason being we knew I was not going to be able to do a lot of the work, and we wanted to find the GCs local pretty easily. So some of the things we did, which I think helps, is we put on a really good hat. We spray foam the roof, but the walls, we let it breathe a little bit. And then so that means we don't have attic ventilation, which was, to me, was one of the things we were looking at was the International Wildlife Urban Interface Code, which one of their features was you don't let vents in your roof let ember in. This is like a building code for buildings that are in wildlife fire hazards. Austin has a lot of those, and that's kind of how I stumbled on it. And so you don't, instead of just having your soffit vents on your eaves exposed, and we had deep soffits. I mean, we had deep eaves because we modeled the house for that site so that we could optimize the sun and all that. And all that vent we would put screening on. I think the size is 1/8 by 1/8 of the mesh, like, so that the embers don't go in and start your attic on fire. At the last minute, because of the pricing, we realized we would just spray foam the ceiling, the whole roof, and we splurged. We spray what savings we had on spray foam. We spray foam the garage because there we didn't really care. We just wanted an insulated garage, so we had really good temps in the attic, and then the walls could breathe a little bit. It's not as plastic tight, which is what Adam was referring to. Um, and then some of the other things we did, the lowest 2 foot of my sheeting, we tried to do pressure treated plywood to improve against rotting and moisture and termites. So I think those were useful. So we did do stick frame. It was just we had to find how can we make this building perform better than conventional that you see nowadays, where it's practically cardboard on the sheeting. So.
Yeah, you mentioned something very important, which was the fire, right? So most people don't realize that embers entering the attic space through the soffit vents is the number one way that buildings catch on fire in wildfire events. So the number one cheapest thing you can do if you're in a wildfire area, by the way, still, the metal roof. Okay, and then make certain that the soffits are properly equipped to not let embers get up into them, and that those two things by themselves greatly enhance the resilience against wildfire of a house. So just be aware of that. The insulation, most of these insulations, they're all petrochemical products, and they all off-gas certain volatile organic compounds. So for a while they have a high off-gassing profile, and I try not to use them when I don't have to. The reason they become so popular is this: you can get teams to come in and just do multiple houses at one time. Developers love that. They can bring a subcontractor in and just spray. The other thing that's important to realize is that if you spray it right, there are no air gaps in the corners. Like when you put in between stick framing, one of the biggest problems you can get with bat insulation is that there can be air seams in the corners. Does that make sense? Like in the back corner or between where you put the drywall. Please don't put drywall. Or whatever your drywall replacement is. There can be little air gaps, and in that space, what can happen is you can get convection currents happening. You can get the hot air starts to rise up. Okay, and it's gathering moisture. If you're getting moisture into the wall, it can gather that moisture. And when it comes up, then what starts to happen is it starts dumping its heat and starts coming back down the other side. And as it does that and it cools, what does it do? Dumps its moisture, it condenses. So you can get, if you have those air gaps in your wall, you can get condensation, especially towards the bottom of the wall where that cool air is falling and condensing and so forth. This can, of course, create mold problems, and it can create rot problems, right? So one of the reasons people love the spray and foaming is if you do it right, it gets every little nook and cranny in there, and it stops those convection currents in the walls. Okay, there's of air moving, right? So we're really careful if we use an alternative to make certain that now what are alternatives? There are alternatives like wool batting can be excellent, and wool batting has the advantage that you can it can handle some moisture, because I don't know, Nicole, do sheep, are they okay when it rains? Yeah, they kind of are, right? Rock wool or mineral wool actually can't handle the moisture very well. So a lot of people are like, oh, we'll just use rock wool. Well, if you do that, you have to be really careful, because if the rock wool gets moist, it doesn't handle it as well. So there are alternatives, and they're not actually that much more expensive. They're more expensive right now just because they're not as common. So you can do it, but yeah, that's what I would say with that. According to how much you like breathing poison, it's just up to you.
First off, I do want to back up the thing you were mentioning about the metal roofs and the soffit fence.
Yeah.
About 3 years ago, in a little bit past where I'm at, there was a wildfire that took out about 375 acres, of which 30 was residential. The only building that didn't burn down was a 60-year-old building with a metal roof that just had its soffit fence redone. So that's a big deal.
Yep.
Main question kind of goes back to an earlier one for you about your highly technical books.
Yeah.
As someone who basically considers white papers light evening reading,
Yep.
but also has to sign up for anger management when I think about any kind of formal education, do you have any suggestions for things that could lead to a forward career path in your kind of design that doesn't require licensing, that has college in front of it?
Yes. There's a lot of amazing resources. You're looking at the built environment, like buildings and stuff like that, or you're looking at okay.
More of the design aspect to it.
Yes.
But if the building is involved, I don't mind either.
Okay, cool. I won't go through the whole list right now, but I'll come and I'll sit down with it. I will say everybody should probably read Christopher Alexander's A Pattern Language. That's pretty amazing. I have all kinds of stories about that book. There are several others out there that, according to what you want to get into, I can make specific recommendations. But there are some amazing book resources out there now. If you don't, and we're about to release, I'm the primary author on the biocompatible design standard. So we're about to release the biocompatible design standard probably early next year. And so if you want some light evening reading, you could go read the biocompatible design standard. And it'll tell you how to build, how to make human technologies that are deeply compatible with a living Earth.
If it's technical light reading stuff anyway, FEMA has some useful things as well. Not that it's natural building specific, but you can gain concepts on it. Like ICC 500, I think helps you design storm shelters, tornado shelters. There's a flood design guideline from FEMA as well, which locating your property, if you are in the flood zone, how you can mitigate it, like how your walls can drain better if you get hit by a flood, for example. And since you're already at it, read the building codes, the residential code, the wildlife urban interface code. It'll give you some interesting ideas, especially the appendices in them, where they just focus in on how to apply it instead of like certain jurisdictional gibberish.
Something interesting. I know. Did anybody flinch when he said FEMA, by the way? Here's what's interesting about FEMA. It seems that their operational side and their theoretical publication side don't talk to each other, because you can go into some of the FEMA publications and you're like, who wrote this? This is actually really good. And then you go look it over and you go, these are the operational. Did you read what your other team? No, we didn't read that. We don't. Like, I pull out some of the FEMA stuff and here's your own publication. Can we just go by that? And they're like, we've never seen this before. Right. So I've had to go have fights with FEMA on numerous occasions. It's like in Western North Carolina after Helene, oh my God. And then, after Lahaina, and when I was responding with bioremediation to the fires, it's like all that stuff. It's like, oh my God. So it's really interesting that FEMA does have some really good publications, but their ops people, sometimes they're helpful, but other times they just maybe not quite so helpful.
Also, sorry, the other night I realized FEMA, they have an email that you can ask if they offer grants for your county. So that might be something to check out. I'm checking out my location because we have one. We want to use the funds to rehabilitate the existing one. So
for
northern environments, think Idaho, Wyoming, Montana, what natural building techniques would you recommend there?
Are you? Yeah. Yeah, you can just go do a wafati. There you go. So where you are there is annualized thermal inertia really works pretty well in those areas. And that's actually most of the work on annualized thermal inertia has been done in those environments. When I've done annualized thermal inertia work, I've had to actually extrapolate from research done in those regions. Because like the passive geothermal tubes and the way I'm doing the thermal mass of the building coupled into the earth with the perimeter insulation going down. Well, where you are, what's your frost depth? Okay. So we're like Montana-ish? Yep. Okay. So you're
30
probably
foot.
5-6 foot frost depth, worst case. Okay. So we have to actually go down below that frost depth with our vertical insulation. Okay. So I'm probably going 8 feet with my vertical insulation. It's pretty significant. But when you do that, you actually create this big thermal mass under, and it becomes a thermal flywheel. And then you can do passive geothermal. In those areas, we typically do about one passive geothermal for about every 300 square feet of building space. And that I have some diagrams I can show you with that. That actually allows for that. Rocket mass heater, you're definitely in rocket mass heater territory there in that area. And that area also has high diurnal swings if you're inland, like in Montana. Even in the summertime, your night temperature can go down into the 40s. Like it can be 103 in the afternoon and the sun goes down and you're like, what just happened? It's now 45 degrees outside. Use that to your advantage for cooling a building, right? So you're going to use that cool of night. And so you use that diurnal swing. And if you do it right, you can pretty much build buildings that don't need mechanical cooling. What they need is they need to just have good ventilation. And then you cool the thermal mass and keep it cool inside. So, yep, you can still use hempcrete. You can still use, things like that. You can use straw bale even up that high and so forth. Those are all good things. But what you're going to do is you're going to use that to your advantage. And what you're really up to there is you're up to keeping the warmth of the summer for your winter. When you're down south, you're up to keeping the cool of the winter for the summer. Like around here, Jack, what are you more worried about? Cooling things down or heating things up?
Cooling
things down. So when it's cold in the wintertime, you're going to capture that cold somehow and use it later. You're the opposite if you're going to be up in Montana. You got an awful lot of cold and less warm. So you're more concerned about capturing the warm and then using it when it's cold, right? That's and so you're just taking the strategy and reversing it.
What's really crazy in those climates to me is how cool it seems like it is when it's 100 degrees out.
Yes.
I was up for a workshop with Dave Jackie in Helena, and we were surveying the site, and all the students were talking, mostly were from Montana, how hot it was.
Yes.
And I'm like, it's not hot. And they're like, they think I'm jerking their chain because I'm from Texas, And I'm like, well, what do you think it is out right now? And the one girl said, it's almost 100 degrees. It might be over. I'm like, get the hell out of here. I put my phone out. It was 101.
Yeah.
And it blew me away. It was 101 degrees. And I'm standing there in jeans and a t-shirt, no sweat.
No sensible perspiration is what we call it. Yeah. You had no what we call sensible perspiration. Remember, comfort is a combination of temperature and humidity, right? Because when you are in regions of low humidity, this is when your sweat system is very efficient. And what will happen is it'll be 102 degrees outside and you have no sensible perspiration. What that means is you can feel it and you're like, I don't have any sweat beading on me. Well, of course not. It's evaporating the instant it comes out your sweat gland and it's carrying a lot of heat away. And therefore your sweat glands, they're doing their job. Now, that'll dehydrate the hell out of you super fast. So you better be drinking a lot of water. And if you're not used to that environment and you get into it, it'll dehydrate you before you know what's going on. People who lived there, they learn better, right? But if you've lived in muggy South, right, now all of a sudden you're in a system where your perspiration when you're outdoors is not very effective. You sweat, and your humidity is so high that it really takes a lot, and it's to get that to evaporate and carry heat off of you. That's why 101 degrees in Alabama or Texas feels like you just stepped into Hell's Kitchen. And then you go into a place, it's 105 degrees and it's super low humidity. And you'd think if you grew up around here, oh, it's maybe in the 90s, maybe upper 80s. And you're like, this is right. Okay. That's what's happening, right? So this is why comfort standards always refer to both temperature and humidity, because that humidity modulates the feeling of comfort tremendously. And so that's what you're running into. And that's why when we moderate the inside of a building, we're actually controlling both the humidity and the temperature. And there's these narrow ranges that that ASHRAE, who's familiar with ASHRAE? ASHRAE comfort standard. Anybody know the number? Okay, you can go look that one up. I think it's 93.1, isn't it? They changed it 2 years. Okay, the comfort standard. It actually, like, I'm supposed to know that because it's part of the well building standard, and also part of LEED. But they specify both the humidity and the temperature of the building because of that comfort and the sensible temperature.
Jack is actually in a really unique spot. The
Yep.
standard cuts almost straight through this property going towards Dallas.
Yep.
And he's on the line of it's not worthwhile to use free cooling because the speed is so high.
Yeah.
This particular line, and he's right on the line of just saying it's not even worth your time to try to keep cooling.
Yeah. Yep.
How do you feel about using green lumber for your structural part of your building?
Say it one more-
Green lumber.
Green lumber.
So you talk about site sourcing and things like that.
Yes.
If you don't want to wait
Yes.
an inch per year or whatever for drying.
So here's my thing. If you're doing timber framers have several centuries of experience doing greenwood timber frame. I have this tendency that when I do timber frame buildings, I don't embed the timber frame in the wall structure. I put a curtain wall around the timber frame. I put the straw bales around. I do not embed the timber frame into the straw bales. Same thing if I'm doing hempcrete. I'll put a curtain wall around, and I'll actually put a small amount of space between the timber frame and now. So, yep, we've done lots of greenwood timber frame that way. And because we're doing that, we're flying the timber frame off of the curtain wall. Any small moving, checking, cracking it does, no problem. Do I want to bury that in the wall system? Now I'm getting a little more concerned, right? Now I'm getting more concerned. Would I do greenwood lumber like stick? Oh, hell no, right? That has to be cured, right? You need that to be kiln dried and everything else, because that stick-built timber frame, stick-built lumber, that system is dependent upon dimensional stability. And if things, yeah, so, and you're cutting it down to where it's easy to warp and, right. Yeah, exactly. It's all it'll create a mess. So yeah, we've done greenwood when we get the Timber Framers Guild in and we're doing timber frame, and I design it so that the timber frame, because the timber frame, if you've done well, it's beautiful, right? So for long-term buildings, I want to be able to take the curtain wall down and replace it if I need to. If I ever need to replace the straw bale on these buildings, timber frame, when we're doing these big, huge timber frames like this, those can last hundreds and hundreds of years. It's like, sure, if I need to take down the straw bale wall and replace it, okay, after 200 years, no problem. The timber frame is not touched; it goes right by it. That's what I end up doing. So yeah, rule of thumb: greenwood timber frame. If you have timber framers that know how to work with it, beautiful. They'll also peg it when it's green, and then as it cures, it locks in. And that's actually the technique, right? Because we'll do timber frame buildings that are like have no metal in them at all, like in terms of the fasteners. They're all dowel fasteners, and they'll they'll put those dowels in green and let them actually cure in place. That's great. Don't try it with a stick-built building. You will not be happy with the results.
How do you feel about old school traditional triple width masonry construction?
I don't know if you have any thoughts on that. Okay. You mean for exterior walls or for using basically what, stone or brick?
Either.
Okay. They both can be good exterior claddings. They're highly durable, but to me they're exterior cladding, right? They're not really insulatory, so they don't give you that. And most brick, there's a reason that they got to going with brick sided buildings. What you normally see right inside of the brick, you have the vapor barrier, right? Because the brick isn't really effective as it will breathe. It will let the vapor in and out. So they can be long-term cladding. Trying to think of what else to say about it. But then you need to think about what the rest of your wall structure is inside, right? They're not structural usually unless you get pretty heavy. The way the Masons do it today, they used to have structural walls that way. Okay.
That's kind of more what I'm referring
to. Oh, you're talking about the structural
yes,
walls.
Sir. Yeah.
Okay.
Yeah, like the old traditional masonry where it is all stone.
Yeah. So yeah, it's exactly. Your problem is that you have high, you're getting castle walls. So if you're doing that, what you're getting is you're getting a wall with very, very little insulation and with some thermal mass. Okay. So if you're in a cold environment, now you're fighting with cold all the time. It's like when the winter sets in, you got no thermal mass, those walls get cold, and now they're basically sucking heat out of the room because they're a thermal sink, right? And so now what you're doing is you've got your fire going in there, which is radiantly heating you. And so this side is toasty warm. Your backside with the wall behind you is freezing cold because it's sucking heat. How many of you have been out camping, right? And you've got the ground underneath you, and you've got your nice big thick ground pad and your sleeping bag, and you roll over and your hand just kind of like isn't hitting the ground, but it's like a couple inches above the ground in your 20-degree sleeping bag. And you wake up and your hand's about to freeze. Anybody had that experience? Yeah, what's happening is that cold earth is literally acting as a sink, and it's sucking the heat out of your hand, even though it's not touching, right? That's what happens with those cold masonry walls. That's why castles had those enormous fireplaces, and everybody would get really close to the fireplace, right? Right, and they would have tapestries on the walls to keep that from sucking the heat out of you, right? So those kinds of things, high thermal mass, low insulation, that's where you have high diurnal swing and you can modulate it out. But then you're back to that whole thing of how thick and what's the material and everything else. I would not use that in a super cold environment or a super hot environment because you're going to be fighting with that thermal mass constantly. Yeah.
So here's one, and I want you to come at this more from a design element answer because I'm sure there's better ways to do it, and I certainly wouldn't consider the building a high quality building. But when I was looking for a place to move back here, and I found this place, I also found a place out in East Texas we looked at, and it had a pretty decent house, but then it had a mother-in-law suite, they called it. It was not, I wouldn't put anybody's mother-in-law in this place because it was a decrepit old single wide.
Yep.
But it didn't have a standalone AC system. It had a couple window units in it, but they were not being used at the time. And we walk in, and there's just some box fans and windows. And I walk into it, and it's a single wide trailer, and it's old.
Yep.
And I would not have wanted to sleep at that temperature, but it was much more comfortable than you would have thought. Up over top of it is like an awning metal roof on about a 4-degree pitch, like that. And then I started looking around. It turns out this was actually very common in rural Texas. They'll take these little mobile homes and do that. You would never be able to do it with a house like mine. The size of the structure, one good windstorm, it's a giant wing.
Right. Wind
But-
sail. Yeah.
The thing that impressed me the most wasn't just the temperature, because it was about 100+ degrees out, and it was reasonably decent in there. Like, you could stand around and talk and not want to die.
Yes.
So I go and find a ladder, and I climb up and look at the roof. The roof looks like somebody put it on yesterday.
Yep.
Right. So I managed to track down the owner. I'm like, sorry, dude, I'm not going to be putting an offer or nothing, but I'm curious about this. When was that roof put on that trailer? He said, well, we re-roofed it back, I don't know, 15 odd years ago, and that's when we put up that canopy. It had been there 15 years, and it was cheap asphalt shingles. You know that what they look like at 15 years. They're
Yes.
falling apart.
Yeah.
So between not just the thermal advantage, but the protection of the roof, have you ever
Yep.
used design elements like that?
Yeah. So there are Scandinavian design systems that actually use an approach of a building inside of a building almost. Anybody seen those before?
I've seen those.
Yeah.
I know what you're talking about.
What they're basically doing is they're putting an external shell around the building, okay, including a roof that flies over an inner roof, and they're using that as a buffer, and they actually circulate air and convection around it, and they use that as a method. So that approach of what we would call a stacked roof, where you have airspace in between, and you use convection ventilation. What you do is you have a ridge vent at the top, so when the heat comes up, you literally get a chimney effect, and it draws fresh air in, and then it picks up the heat from and goes up and out. That you get this constantly sun-driven convection current that's pulling fresh air in across your roof, right? And you can do this low tech, like with the mobile home, or in an extreme environment like Scandinavia, you can do it as an integral element to the house and literally have space underneath the building where all this stuff circulates. I won't get into all of it. There's all kinds of really sophisticated things you can do to circulate the air around the outside of the building and do what really amounts to certain forms of thermal inertia and passively driven convection heating and cooling. And so you can go from really simple, like hang a tarp over your tent. Who's done that one before, right? You know what happens when you hang a tarp over your tent? It's like, wow, this is much better, right? For a number of reasons. Even in cold, it gets better, doesn't it? Why does it get better? Well, because frost is a phenomena of loss of infrared radiation to space. Okay, the more you can see open space, the more heat you will lose at night and that's how you get frost. If you just move your tent under the canopy of a tree, even if it doesn't have all its leaves on it, if it does have leaves on because it's evergreen, what happens to your heat loss from your tent?
Yeah, it goes
It's
down.
way down.
Because you got we call it a frost shadow.
It's a frost shadow. You're in a frost shadow. So what you're doing is you're actually creating a frost shadow in the wintertime over your head as well. So it actually works in the wintertime to actually keep you warmer, not just in the summertime to help keep you cooler, right? So it's a technique that can be used in extreme environments. It will also can be used in hot deserts where the sun is really intense. You can do the same thing. Yeah.
Okay, I wasn't going to ask this question, but there's nobody in line, so now I get to.
Well, we got he agreed to ask a question. He's got a question. He's got to ask a question. Go get in line.
Come on up. I'm going to ask mine. So, this is kind of selfish, but may apply to other people. I live in a very rural county that has just become aware they should maybe have codes and zoning.
Yeah.
And they have no idea what the fuck to do.
Yep.
We already have an inspector, and he has no idea what the fuck to do. And next week there is a hearing where you can give feedback.
Yes.
How would you advise a person to bring in concepts of natural building into that, just sort of preemptively? As much as I don't like engaging in politics,
yep.
What would you say about guiding them in that direction? Because right now we've assessed their hearts are in the right place, but they are leaning on the usual propaganda-filled things.
So
you do not need codes.
we've had to fight this fight before, and the thing you have to remember is that why do we have? Hey, here's the question: why do we have rules?
Because somebody did the dumb thing first.
Exactly right. So the reason that this is the same reason that codes get written, right? You know, you look at every element that's in a code, and the people, if you go back to people who wrote the code, you say, why is that there? All said, you know, ask me why. And they have a story for that, right? So when we go in and we start working with code officials, we have to acknowledge that, yep, there's a reason that that was written that way because people were doing really stupid things and making big problems. And so, you know, it's kind of like, yeah, you get to a certain level of complexity and the people around you get to a certain level of cumulative lack of wisdom, and that now all of a sudden building codes emerge. That just kind of happens. But fortunately, IBC, International Building Codes, have started to incorporate this. So there are some elements in International Building Codes that are really good. What I like to do is basically get them to say, hey, we understand why these building codes are here, but they can possibly keep us from doing some really great innovative things. So could we put into the regulation that you can do anything according to International Building Code and so on and so forth, and you can get an exception by having a professional engineer sign off on the design. So what that's letting us do is, if I need to come in and you're like, I want to do the super innovative thing, okay, you can call me and I'll go, what are you wanting to do? Oh, okay, I'll go find the right professional engineer in that field and we'll sign off on your exception. Now what that's doing is it's giving you the capability of doing smart things, a little extra due diligence to get it so forth, and without having to go back and fight them to get like the law changed once it's in there. That's right. Yes. So those kinds of exceptions, like if we are working with somebody who really is what they're doing and we're going to try something innovative and whatever, and they sign off on it, we can try it. Okay. And what we do is, we've been able to get stuff like that in. What we do is we go in the door and we want to do anything innovative. I want to go talk to the code officer on day one. And here's my whole thing. Mr. Code Officer, here's who I am, here's my qualifications, here's my team. Okay. We understand, you know, we want to come and start working with you on day one because we want to do something innovative. Okay. This is cutting edge. We got a team behind it and so forth. We know we need to work with you. We know we need your help. Okay. In order to get this done, we're going to try to use this exception and so forth. We need your guidance on how to get this done properly. Okay. Now what's happened is you brought them in as an ally before you even start. Okay. Now you're going back to them going, we're thinking about this. Here's what our professional engineer structural person's saying. Here's what this is saying. What do you think? Right? Oh, right. And then they're like, well, I have this concern. Huh. Okay. Well, how do we answer that concern? Okay. It's a little extra overhead, but we've walked people through some pretty crazy things that way because we got them involved at the beginning. What you don't want to do is show up and go, yeah, exactly. That, or, you know, we did this thing and now we want you to approve it. And they're like, you did what? You didn't come ask me? What are you talking about? No, we're not approving that. You got to tear the whole thing down. So that's what you want to avoid, right? Yeah.
What I like about that's like stacking technicals and strategy together, right? And so if you can get that exception clause in there, then the rule follower can follow the rules, and then you use the strategy to get it further. But the other thing you might look at is some of these specifications that Alan's talked about for these different building types. You know what bureaucrats love? Really cool shit they can take credit for that they don't do any work for. So I don't know if you remember the show I did with the guy from Colorado about how boilerplate codes are causing problems. That's your concern, that somebody's going to boilerplate bring that code in, and all of a sudden stuff that never applied where you lived, and somehow nobody died for 150 years because of any of these things, is now not okay anymore, right? So what you can maybe try to do is bring in some of your own boilerplate, like add this, because you don't really care what they say about a stick-built typical suburban home, but you're worried about what you can do with a straw bale, or you're worried about what you can do with a round house, right? That was one of my, when I moved here, a property I absolutely preferred, had a really great price on, but I didn't have enough money to just bring the cash, was a circular home. It was 4,800 square feet. It was on 7 acres in beautiful black prairie land clay. The kitchen was probably worth 65 grand by itself, and it was $245,000. I'm like, let's go. We could not get it appraised because it was freaking round. No, it wasn't a geodesic dome. It was just it wasn't really round. It was more like an octagon shape that they had built. It was built sticks. It was amazing. They wouldn't appraise it because they said there was no comparables to appraise it against. But the city of Mansfield and the county of Tarrant had no problem sticking a value on it to tax it. But we couldn't get a conventional FHA, VA, anything like that on it.
So I think I'm in sync with what Alan is trying to say, and Nicole is saying she needs this by Monday. So a lot of zoning codes will say will have a special purpose district, and then over there's different regulations. But you don't, like you said, it looks like their heart is in the right place. Right, which is good. It's good. He needs guidelines, right? And as a community, you can put some pressure on him instead. But you can't define a district because now you kind of exclude some people, right? But the idea is you could put in some language as they put the zoning together, special language for what's that word? Special design structure, something like that, so that there's language in the code that if you meet, you then fall outside of this the typical codes, and you just have to qualify, and you can add to it by, hey, as long as it's stamped by a licensed professional, and I can show you that it's going to meet. I'm doing all my due diligence. It's all meeting life safety codes, but you have the language that it's kind of like when they write the language for the zoning. You help them write in a way for more creative experimental stuff in there, and then you'll come and say, when we finally do know what we're going to do, because we don't know yet what it is, we'll come with the professionals to help us finalize it. So
keep in mind that it's all about liability, and with
Yeah.
engineering stamp, that liability
Right.
is very expensive.
Yeah.
You said drywall was bad, and
Yeah.
if that's so, why is it used in so many homes?
Because what ended up happening was it's cheap and easy to manufacture in huge quantity, and they got it really standardized where a team can go in and put in a huge amount of drywall in a pretty short period of time. They have the tools and everything else, so it's like it's cheap and easy, and it can also be used in commercial buildings and in residential buildings. And so I watched a team come in and put drywall in 660,000 square feet of commercial building that I was responsible for. I didn't design that one, but I was responsible for the labs in it. And the team came in and put in 660,000 square feet of drywall in a month. Like, I'm talking about like a building, the 660,000 square feet. They just blasted through it, right? It was the metal stud. They just blasted through the whole thing. It's like you can get a team in there, just crank. And it's not high quality. It's not why they do it. It's not durable, as anybody knows. It's not that. Okay. Yeah, exactly. You bang up against it and you punch through it and so forth. It's just so bloody cheap and it's so fast that that the contractors loved it. They could just bring in a sub and have have a house done like super fast. And so it was really easy, and therefore it just got standardized when they were kind of standardizing the way you build a single single family dwelling. It just kind of became the default, and then it got picked up in commercial, and there you go. And now it's everywhere.
To put it in perspective, Bray, back when they were doing this in the 1945 forward, right after the war, they were building 2 and 3 bedroom houses that were selling for $7,800, $15,000 in that range for a 1,000 square foot to 1,200 square foot home with either a carport or a garage. So they were trying to industrialize it like an assembly line, even though you don't have a factory. You kind of like you're making a mobile factory pushing things out into the field.
Yep.
But I got one more question for you, and we're done. I don't care. Okay. It's my place. It's my time. Because it's just an interesting one because you're an engineer and you also know a lot about chemistry. Is there a way that if we wanted to make something that would work like drywall and we could produce it in, maybe even a little bit more money, but we could produce it rapidly, install it rapidly, we could make something that would serve that function, but it wouldn't have the problems. And it would look good too, because you want it to look good. You don't want it to look like that beaded shit they used to put in the mobile homes. Because when you said gypsum, it just tripped. Like literally, I add gypsum to things to feed fungus. This cannot be good.
Yeah, and that's the whole thing. That's why we mentioned the concrete fiber board earlier because of fire rating and so forth. So there are some people doing some really interesting things with products that basically precipitate out very similar to certain forms of stone, like basalt. And so we've been really interested to see, like some of them have been able to do extruded panels that basically are extruded from basalt, which is quite interesting. And these are incredibly rugged. They could last for hundreds of years. And since they're basically a basalt chemistry, we could produce them at large scale for pretty cheap once we got it set up. Interesting. Who's heard of the extruded basalt rebar, by the way? Anybody worked with that before? Exactly. What you're seeing is that they're doing these extruded basalt rebars. They don't corrode. Okay? They don't corrode. What's the number one reason for concrete failure? Rusting of the rebar, right? So where we're going these days is we're going to get rid of any metal rebar, and we're going to go to extruded basalt rebar because that extruded basalt will not corrode. And there are groups that have prototypes of some of the better extruded basalt rebar, and it's already on the market. But they've got stuff that the problem is it's too strong. And literally the problem is that it's so strong that bending it in the field is really difficult. And so we kind of went through with them how to create in the factory pre-bent 90s so that you could do the pre-bend and tie-in and so forth. So it'd be field expedient. So this stuff is coming, right? And so you're going to start seeing that pretty soon. You're either going to when you pour concrete, you're not going to put steel rebar in it. You're going to put like an extruded basalt, or you're going to put it, or in some cases it's going to be fiber. The fiber additive instead of rebar. But in the cases where you would use rebar, you're going to see that. But there's these alternative chemistries coming in the material science where we're looking at materials that are analogs to natural materials that are completely non-toxic and that can last a long period of time. The material science is now catching up. So I'm thinking that we're going to see increasing. We see more demand, right? We just need people to demand. Hey, we're over drywall, and we want the alternatives. Yeah, okay. And that the one other thing I'll just mention nobody's asked about is if you're not thinking about the EMF RF environment inside your buildings, you ought to be. Okay, I don't know if you thought about if you looked at that. Yeah. But yeah, I also look at the EMF and RF environments in buildings as we build them. So that's something else that's in the biocompatible design standard because nobody's looking at that and they ought to be. So I'll just leave it at that. Yep.
All right. Thank you so much. Where we go from here are some breakout sessions and dinner and barter blanket tonight. So collect your